Hello student to the Foundation of Classical Electrodynamics course. So, under module 2 we have lecture 44 today, and today we will going to discuss about the displacement vector. We have class number 44 and today we will going to discuss about the electric displacement or the displacement vector. So, we find that within the dielectric the total charge density, the total volume charge density is the contribution of the two kind of charge. One is we call free charge and another is the bound charge. You may remember that the bound charge already we find that it is the minus of divergence of the polarization. When we have a non-uniform polarization, in that case if I make the divergence of that polarization vector, then that leads to the negative value of that leads to the amount of bound volume charge density. So, in general the volume charge density rho can be divided into two parts. One is free charge density, volume charge density, and another is the bound volume charge density. Now, in the Gauss's law, what I find, the Gauss's law says that epsilon naught and then divergence of E is equal to rho, right. Divergence of E is equal to rho by epsilon 0. I just multiply this rho here, epsilon here, and write left side rho. So, this rho is now rho free plus rho bound. Already I write that rho bound is a divergence of minus of divergence of P. So, I can write that epsilon 0 divergence of E is equal to rho f minus of divergence of P, and that quantity if I put this in this side and put this epsilon 0, which is a constant, inside the divergence operator, then I should have divergence of epsilon 0 E and then plus P is equal to rho f, right. So, this quantity, this new quantity, we call this new quantity, whatever we are getting here, we call the electric displacement or displacement vector. We defined it as D, which is equal to epsilon 0 E plus polarization P and that we call the electric displacement or displacement vector. So, the formula, the Gauss's law is now modified for D, and now we are having the divergence of D is equal to free charge density rho. So, if I now write this expression to the integral form, then the integral form leads to integral form give us that the closed surface integral d dot ds should be q in qf enclosed. Mind it, we have side by side. So, for electric field we have this expression when there is no dielectric material. So, I have rho divided by epsilon 0, and also we had the flux of the closed surface is simply q enclosed divided by epsilon 0. So, now for the d the expression is changed, epsilon 0 is absorbed inside d, and we have an expression that the differential form of the Maxwell's modified Maxwell's equation is this, and this is the corresponding integral form. Now, as I mentioned that divergence of E is rho by epsilon naught, and divergence of D is rho free. Now, if I look carefully, the curl of E is 0, right. Now, the question is, should I write the curl of D to be 0? So, what is this value? Should I write it 0? The answer is no, because I should have a quantity like curl of D is equal to curl of epsilon 0 E plus P, because D here is epsilon 0 E plus P by definition. So, this curl gives us two quantity, one is epsilon 0 curl of E, which is definitely 0, plus curl of P. Now, even though this quantity 0, this quantity is not equal to 0. It is not necessarily that curl of P should 0. So, in general I should write that curl of D is not equal to 0, mainly because of the fact that curl of polarization, which is arises due to the dielectric property of the material, is not equal to 0 in general, and that is why curl of D is not equal to 0. Since curl of D is not equal to 0, then we can also argue that D cannot be expressed as the gradient of as a gradient of a scalar function or scalar field, which we can have for E, right. So for E, what happened? The curl of E was 0, and that leads to the condition that E can be represented the gradient of something, and that we call the potential. This is the consequence, the fact that curl of E is equal to 0. That means E can be always represented in terms of gradient of something, but in case of D it is not possible. So that means there is no such thing called potential for the vector D. There is no potential for D. There is no potential for D. Okay. So, we have a very brief understanding of the displacement vector D, and now we will, based on that we will continue few things. So, that is we are going to understand once again the susceptibility, and then the permittivity of the system and the dielectric constant. These are few well known terminology. So, we need to understand once again, because we have already discussed about the polarizability and polarizability tensor etc. in last class. So, and also understand just now what is the displacement current displacement vector. So, with the base of that, let us understand this. So, suppose that we have an electric field here, and for the dielectric system what happened, a dipole, a induced dipole is induced like this. This is the electric field, and we have plus here and minus here. So, some induced dipole is there, and let us consider the P, the polarization is proportional to E, and that is when E is not too strong. Obviously, if E is too strong, then I can write it in this way, and in the scalar form I can write that P is equal to epsilon 0 chi E. This is the way we can represent. Earlier we represent in terms of alpha, but now I write in a different way, because that leads to this terminology susceptibility, permittivity and dielectric constant. So, this is the way one can write in general. So, here this epsilon E, this chi E is called the electric susceptibility of the medium. It is called the electric susceptibility of the medium. Okay. So, for linear medium where this quantity is no longer a tensor quantity. So, we should have like the like the polarizability tensor. So, here we should have the susceptibility tensor in general form, but let us consider the medium to be linear. So, we will say that this is simply a scalar quantity. In that case, my for linear medium, for say linear homogeneous kind of medium, we have a straightforward relation that D should be equal to epsilon 0 E plus P by definition, and my epsilon 0 E, I can write it, and then P I write in this form. So, it becomes epsilon 0 chi E E. So, if I take epsilon common, then we have 1 plus chi E and then E, and D and E, this relation now we can write in this form. It is epsilon E, where epsilon is equivalent to 1 plus chi E. Now, this epsilon, whatever the epsilon I is called the permittivity of the system. Okay. The ratio, normally we have epsilon is equal to, which is equal to epsilon naught. Okay, here I should write an epsilon naught. So, epsilon naught multiplied by 1 plus chi E. So, the ratio we called the relative permittivity or the dielectric constant, and that is represented by epsilon divided by epsilon 0, and that is simply 1 plus chi E, which is a number because this is a ratio of two same quantity. So, this is called the relative permittivity or dielectric constant. Okay. So, now in the light of these definitions, so we can understand few more things, and that is when the dielectric is placed in a medium. Already we discussed this issue, but let us consider this once again. So, say dielectric placed in a uniform electric field. So, what happened? So, suppose I have uniform electric, how I get first, how I get this uniform electric field, that we need to understand, that how to get this uniform electric field. One simple way to get this electric field is, suppose I have a 2 capacitor plate like this. So, this is a capacitor plate and we have say plus charge here and say minus charge here. So, in between I can have my electric field which is uniform, and this electric field, the value of this electric field is simply sigma divided by epsilon 0 along the direction n, if this is my direction n. Now, in this uniform electric field, now I am going to place the dielectric. So, what happened that this figure I have already drawn in a different way. So, this is the plate and the plus distribution is this, and a dielectric material is placed, right. So, this is my dielectric material that I placed in between this, so that it will going to experience a uniform electric field. So, tiny dipoles are going to one can find this kind of tiny dipoles. Okay, and we have like we have like plus minus plus minus plus minus plus minus plus minus plus and so on. So, tiny dipole will be induced under this uniform electric field, and the figure should be like something like that, right. So, this is the applied electric field which is uniform, and if I write this is E 0 because this is a constant. So, induced dipole field will be in opposite direction under equilibrium. So, this is say E p, that is my induced this is the induced dielectric field. This induced dielectric field will be simply the bound charge whatever it is having, and with this. Now, the net electric field should be E equal to E 0 minus E p, and that is 1 by epsilon naught sigma minus sigma b with the direction of n, and again E is equal to E0 minus EP, and that is E0 minus P divided by epsilon 0, because this bound charge is like P dot n and EP is this divided by epsilon 0. So, it will leads to P epsilon n, P divided by epsilon 0 dot n. Now, P is again epsilon naught chi E and this E, the external electric field that. So, in this case here it should be the E0 is my external electric field, so it should be E0 here. So, E, the resultant electric field is E0 minus chi E and then E this is not E0 because in general the polarization will happen because of this electric field, whatever the electric field we are having here, the net electric field, and eventually we have E as E0 E has no, it was E0 not so, because the field is produced by E0. Yeah, okay, I noted, I put it here E0 not E. E I represent as, okay, because I should this is the uniform electric field and I write the uniform electric field in so this is the net electric field. So, I can write that uniform electric field should be like something this, okay, that is the confusion I am having here. Okay. So, now I can have this expression no, yeah, now I can have this expression where I should have the relationship between the electric field and that leads to, you know, okay, let me erase this. So, I am now having, okay, let me go back and check it, because this nomenclature is something we need to careful. So, okay, this is E and this is the E0 I am applying, this is the uniform electric field that I am applying, and this is the induced dielectric which I write in terms of EP, and this induced dielectric field should be sigma b divided by epsilon 0 and it is in the opposite direction, so minus. Now, try to find out the net electric field. So, the net electric field is the addition of these two, since it is in opposite direction. So, that is why I have a negative sign and I have epsilon 0 sigma minus sigma b. Now, E is equal to epsilon 0 minus EP, and EP I now write in terms of polarization because EP is sigma b. Okay, here I am making a mistake, I guess. So, EP is equal to sigma b divided by epsilon naught and then n unit vector, and EB sigma b is P dot so that is P dot n divided by epsilon 0 and n. and now here the polarization that I should, because this polarization should be based on this total electric field that we are having, because this P is generated due to the total electric field that we are having here. So, that is why this should be E here, and now I have the n unit vector. This is the okay. If I write the vector, then I do not need to use this n unit vector, rather I just simply write my E net electric field is equal to 1 divided by 1 plus this quantity and E 0, where E 0 is the amount of electric the constant electric field under which the these things is placed. So from here I can write that E is simply 1 divided by epsilon r and E 0. Okay. So, this is just to show that if I place an dielectric in a uniform electric field, so what should be the how the dielectric will behave, and what is the relationship between the net electric field and the uniform electric field that we are getting. So, the ratio is showing that the net electric field will be reduced by this 1 by epsilon r time of the uniform electric field that is having, and this reduction is due to the fact that we are having here a dielectric that is placed, and this induced dielectric is now in opposite direction, and that is the reason why we have a ratio, and that ratio will be reduced because of the place of the dielectric. If it is in air, then this value should be 1, but if I place a dielectric in between, then I should have something like 1 by epsilon r. So, this ratio should appear because of the placement of the dielectric. So, we will come this again when we discuss about when the two dielectric when we place the dielectric in between the capacitor to increase the capacitance. So, during that time again this discussion I would like to make few problems we will do, and then it will be discussed once again. Now, I will do one thing, that is the final task today, and that is the boundary condition The boundary condition for the dielectric is important, because I have a say boundary here say I have here dielectric 1 and dielectric 2 having dielectric constant say dr 1 and dr 2, and this is suppose my z direction. For the electric field, we already have the boundary condition or matching condition we have, and that condition is E in this figure E 1 minus E 2 dot unit vector z is equal to sigma divided by epsilon 0, and another was E 1 minus E 2 cross z is equal to 0. In another word, the perpendicular component of E1 minus E2, that is sigma divided by epsilon 0, and the parallel component of the two section is 0. That means the parallel component is continuous, whereas the perpendicular component is not. Now the question is, if I know the relationship of the boundary condition of this E, so what should be the condition for D? Because in the for dielectric system, D is rather meaningful than E, right? So I know the relationship with D and E, and that is simply D is equal to epsilon E. So one thing I have here first, that okay, D perpendicular plus D parallel should be equal to, you know, epsilon and then E perpendicular plus E parallel. So for medium 1 and medium 2, for medium 1 we have D1 perpendicular plus D1 parallel, that is equal to epsilon 1 E1 perpendicular plus E2 sorry E1 parallel. E1 parallel. I just divide the entire vector to perpendicular and parallel component, that is all. For medium 2, I simply have D2 perpendicular plus D2 parallel is equal to epsilon 2 and then E2 perpendicular plus E2 parallel, right. So now we can have, I mean, this when we write this vector in component wise, then this component wise they should be equal, and that means now we can write that D1 perpendicular is simply equal to epsilon 1 E1 perpendicular, and D2 perpendicular is simply equal to E2 epsilon 2 E2 perpendicular, and also D1 parallel is equal to epsilon 1 E1 parallel, and D2 parallel is equal to epsilon 2 E2 parallel. So from here, so from this expression we know that E1 parallel is equal to E2 parallel. So that means from here, exploiting this equation, I can simply have that very important equation, that D1 parallel divided by epsilon 1 is equal to D2 parallel divided by epsilon 2, or in other word I have D1 parallel divided by D2 parallel. Ratio of the parallel component of the two these things is epsilon 1 divided by epsilon 2. That means previously if you see that E1 parallel divided by E2 parallel was 1, that means they are continuous, but here we can see that the transverse component. So, we can conclude here the transverse component component of vector D is discontinuous. So, the transverse component of the D is discontinuous, which is in contrast with the electric field E. Electric field, the transverse component was continuous, but for dielectric system the displacement vector is rather important, and we see that the parallel component is discontinuous. What about the perpendicular component? Because from here we can't have any so we can find it in a different way. So, we know this expression, right? The closed surface integral of D dot ds is equal to the total charge enclosed, right. So, that means here this is, mind it, this is the whatever the free charge we are having. Here we have the surface like this, and in order to execute this integral we can find a Gaussian surface, a Gaussian cylindrical surface like this. Gaussian cylindrical surface like this. So, here, so if I now divide my D, say this is D 1, this is, say, what was my 1? 1 is upward, yeah, 1 is upward. So, this is my 1 and this is 2. So, D 1, suppose it is in this direction. So, I can divide into two parts, one is this component and another is this component. So, this is my D 1 vector and this is D 1 perpendicular and this is D 1 parallel. In a similar way, in the downward I can have a component in this and this. So, again this is D 2 perpendicular and this is D 2 parallel and this is the D 2 vector D 2, and this area is delta S. And now, if I execute that, then we find that for upper and for lower the integration is meaningful, and this portion we can make these things infinitesimally small and we can neglect this integral. So, in that case we have this integral simply gives us D 1 perpendicular minus D 2 perpendicular, because in this direction and this direction the direction of the surface is different and opposite, delta S is equal to Q enclosed. Now, Q enclosed means the total enclosed charge. and this total enclosed charge should be the surface charge density, free surface charge density dot the surface area, whatever the surface charge is accumulated in this surface. So, ds will going to cancel out, and we have the relationship like d1 perpendicular minus d2 perpendicular is simply sigma free. So, that is another relation we are having. So, here also we find the perpendicular component of the d is not continuous in this boundary. So, both the component perpendicular and parallel component is found to be not continuous if the two dielectric if we have a boundary for two dielectric system. So, here we have one dielectric and another upper we have another dielectric, and we find that for two dielectric medium, the boundary condition is saying that the perpendicular component and parallel component of the D both are discontinuous, and the amount of discontinuity you can also calculate from this treatment. So, well, today I already finish this discussion. So, in the next class I will start the calculation of the Laplace and Poisson's equation and solution, and do some problem as a tutorial, and then after that we will going to start the next module, module 3. So, thank you for your attention and see you in the next class.